Okay, let's give this a go. It's a long title. That's me. And it's going to be very quick, by the way, because I've got a lot of slides and not a lot of time. All right, so stay with it. The slides are available at the end if you want them. And there's a big appendix, because I like giving appendices out. All right, so very big topic, very short time frame. So we'll look at a little bit behind why secure boot, introduction to it. I'm not going to go into nuances of individual how secure boots work, because there's lots of them, and that's what we'll discuss. There's many ways, and people do it many different ways, so let's look at that one. This is more about things that we've got to look at around secure boot, the fact that this now becomes a team sport the deeper you go, and we'll explain a little bit about that. A lot of bit about shifting mindset from where things used to be and where, in my view, things probably need to get to. And then, what next? Hopefully might derive some internal conversations within companies about what to do next. Now, the one in this one is that these are my views and expressions, okay, from what I've collated. They may not necessarily align completely with other people's. It's going to be in two parts. Okay, a little introduction and then a little bit more about in-depth what we need to look at. All right, so first off, what's a bootloader? It's a means of getting code into a part running. Often, if it's in a basic MCU, it might already be there, okay? It's just something that runs up at the beginning to get the part started, initialize the device. If you're lucky, okay? It might even be in a partitioned memory space, if you're lucky, depends on the device. Some devices, actually, nothing exists. They're ROMless. Everything gets pulled into RAM, so it's got to come from outside the device, from some external memory. That can be done through a piece of hard logic that just initializes SPI to look at 0. And pulls code in. Okay. So what's the problem with that? Well, ultimately, it's down to, well, what isn't right with that if you're looking at a security context? Because everything's in the open. I can't do anything. At best, maybe people check Summit, but if I'm doing a hardware state machine from outside, I probably can't. Okay. So there's lots of reasons why it's great from where things used to be, but not maybe where we need to go. So secure boot on the alternative tries to change that slightly. So the intention then is that I've got something in the device or around the device that can give me some level of integrity that says what I'm about to try and run is valid, it's got integrity, I trust it, it can pull the part up and allow the part to start and do the next level. The intention there is it stops people putting other things in, so it stops the platform being repurposed, stops unapproved software running, hopefully stops devices being tampered with along with other mechanisms, okay? The intention being to start getting to this idea of a root of trust, okay? And it in of itself is not necessarily the root of trust just having secure code, because there's other things that have to wrap around that to get that whole in place. But it's the nebulous, if you like, of a secure by design thought process. Ultimately it comes down to this fact that we have to have this idea of a chain of trust. And so if you look at a simple device to a more complex Linux level platform, there are lots and lots and lots of things that have to get loaded to get us to that starting point of effectively what we'd call main in our code that we want to run. Okay, so behind the scenes, lots of things are being run, but what do we know about them? How do we know that they themselves haven't been tampered with? How do we know that they've got integrity in themselves, where they came from, who the source was? And often, as the case as we'll discuss, we don't actually know that. Okay. So the intention here is that we've got something at the very beginning, this small, tiny piece of code that we trust, that we effectively call our secure boot, that pulls up that first bit of code, that does some checks to validate it, and it can then pull up some more code, which it validates, which pulls up some more things that it validates, and we get this chain ad infinitum. Okay, it gets to the point where we can run, and we get something that we're happy, and we think we know is valid and secure, can be trusted, is reliable, has got resilience to attack, has got all these other things in place. And that's what we're trying to build. Okay. And then we'll look at other things around that shortly that may change that. So that first bit is often what they get called the immutable code, right? The bit that cannot change or should not change. And if it gets changed, that kind of blows the whole process. If it's changed and it can't be entrusted and it hasn't got integrity, how do we trust the rest of the process to actually start? Now, that immutable code often lives, in many cases, it'll live in ROM. Okay, so it's actually put in by the manufacturer. In our case, it would be us. It'll be in ROM in the device. And that, therefore, can only usually be changed with a mask change. So it's got to be right. And if it's not, well, it's got to go back a level. We've got to change the fab. We've got to do devices, and we've got to put a new mask in. Sometimes that could be an OTP, depends on the design. Possibly not a good idea in some cases, depending if that can be attacked. There are options that are coming around nowadays where we can actually lock that boot segment in flash itself. So you can have a section of flash memory which is locked and non-reprogrammable, which allows that boot segment to be changed. So if a problem comes with that immutable code, it can at least be modified and changed to remove that problem. Okay? It's a fairly recent change, if you like, but that's what's coming. That means that if you want to change it, you can. If you want to write your own because you don't like the manufacturer's bootloader, you could. Okay? And depending on the device, and I'll give it an example. I'm talking about a spectrum of devices from really small ones to very, very large complex FPGAs and intermingling lots of concepts here. Ultimately, that's a possibility. Most of those bootloaders will require some level of integrity check, and they're going to go against some level of key, some level of value that says, yes, I can do an integrity check against this with some cryptographic assessment that says, this is okay to run. It passes my test. That has to be stored somewhere. And when we get to high volume silicon, that kind of gets a bit challenging because it gets expensive to put them in certain devices and protect them. So a concept that's been playing around with more recently is to start doing dual segment devices. So we add a secondary device which has got the root of trust element and the secure device which has got all of those tamper protections and memory protections built into it. And we put that as a separate part inside the main device. So all those things start to exist as well. For processors that basically are ROMless or more complex devices that need to come up in a particular way and only ever boot from external memory, how do I do that? There's nothing on the part that starts that process. So these often come with an external platform root of trust type device where there is an external element that gets programmed which does all of those tests on the external memory that's going to boot first. So it dictates whether the part can start after it's loaded. So it's going to do that decision-making process and all of the controls to determine whether what's in that boot memory is valid. Okay? And that can be performed in many cases on MPUs, network processors, all these very high-level systems, including FPGAs. Bonus of that type of system, which makes it quite funky, is it can be done to run multiple memories. So I can then have that issue, so I can do firmware update to the device against the valid signatures for the device, have the last known good image, have the new image. I can even extend that out to have it running multiple processors and building them up with the same platform root of trust, because I'm designing that all into that platform device. So there's lots and lots of flavors, hence the initial slide of saying I can't talk about the individual nuances of one implementation, because there isn't just one implementation to this. All right, there's lots of ways of doing this. If we look at this from a complex FPGA perspective and then go back to that chain of trust, well, I've got multiple things. I've got to guarantee the validity of the IP going into the logic block. I've got processors now kicking in that I need to bring up. I've got to bring up the device itself. I've got to bring up the devices that bring up the processors. And then I'm going to get to the operating systems. And I might be running multiple operating systems. So I've got to bring up maybe two of those. I've got to have an RTOS level device and maybe a Linux level device. And so as I start moving up this chain, I introduce the potential for more and more places for vulnerabilities to leach in. So even though I might have integrity at the bottom end, I actually reach a point when I get to the load of the OSs that I've actually not configured them correctly. And there's lots of work that goes on around, have I configured U-boot correctly to bring Linux up? So I'm not actually bringing Linux up with a vulnerability in that it's valid because I've given it authenticity, but actually it's got a hole in it because I correctly configured it. All right. So all these things now start to hopefully build a picture that this isn't just about putting secure boot on a device and hey ho, everything's great. Okay. Hopefully we'll find that out to be the case. So secure boot is kind of the tip of the iceberg of the problem. The deeper I looked at it, the more I thought about it, the more people I talk to, you go, hey, you know, this is quite a big problem overall. So let's look at the big picture problem from a security perspective rather than secure boot, that's just solved the problem because I've got my micro with secure boot. Might not be the case. So let's try to look at those and go a bit deeper than that in the next part. All right, so some of the challenges that we look at then. So this is all about the industry challenges. What's kind of driving this? So it was interesting, some of the context in the keynotes, and I learned, again, lots of things that I've missed out in the back of my presentation that now need to be added when we get there. I like listening to other people talk about it for what I don't know. I look at this. One of the drivers is going to be this very simple thing. I've got these 3 things I have to meet, which will eventually come into law in the UK, is coming in other jurisdictions as well. So I have the no default passwords, relatively easy to solve. I have to have a vulnerability disclosure, okay, process outside the part. Then I get to things that affect the development process and the device itself, and what do I have to do in the part. And that's this whole firmware must be updatable and for a length of time. Or 2 kind of undefined parameters which have a huge impact. And the way I look at it, and it's in the appendices when I looked at this, that kind of includes about 9 of the other categories that are in the list of 13 tenets for what needs to be in these systems if we look at the things to look at. Because it starts to affect lots of other processes that I need to consider, because if I haven't got this cascade of processes in place, well, actually, I can't say I can put secure software in and do a firmware update that's valid, resilient, reliable, can be put in the field correctly, and all those things I need to say my system is secure on an endpoint that's got resource-limited capabilities. So ultimately, it's down to this. I've got to try and meet this legislative requirement, and if I can't meet that, how can I say my design is secure? So this starts to affect how we look at the device, the business, and the business processes. Sorry for the eye chart and the words. You can have them later. Okay. So behind it then, ultimately, let's look at code provenance. If I don't know what code I'm putting into my device and where it came from, who wrote it, has it got any integrity in itself, what's in there, how do I know that what I'm going to create and build and put into my device has validity and integrity? So I have to think about my development chain now, what I'm going to feed my device. Okay, I can't just randomly pull code, hope it fits because it solves a problem, and then say, yes, it's fine. That goes back to actually some of the discussion this morning about software itself isn't responsible, but the people who put it together are. Okay, where does the buck stop? If I'm going to have to update or have a connected system, and this has been around for as long as I've been thinking about network systems for 20 plus years, if it's connected, it's inevitable there will be a fault in there. Okay, if 70+% of code's got bugs in it, it's inevitable I'm going to need an update on that device. A firmware update will be required. How do I do that? What mechanism is in place? How do I ensure that the correct mechanism is used, that people don't abuse it? Back to this, what code do I use? How do I check its integrity question again? How do I guarantee what's in my device? How do I let the device know, hence back to the secure boot, how does the device know that the code I'm sending it is valid to run? I've got to build up this trust chain, not through the device itself, but all the way through the business processes that we run. And then if we look at how long for, well, okay, how long is the piece of string? The impact on a development cycle of a bug coming in and a vulnerability being found in the field and a time scale in which you now have to fix it, and the downstream impact of current project development is huge. So I have to look at ways to either mitigate that in the first place by having good design practices to begin with that limit the potential for vulnerabilities, that limit the amount of time that it will take to mitigate those if they do show up, or when they show up, should we say, and also try not to restrict the knock-on effect on the developers trying to create the new products that keep the next pipeline going. So there's all these different business interactions that kick in that we need to start thinking around. So it comes down to this thought that ultimately security isn't just a problem for the developers and the security team. Okay? It's a whole business problem, because somewhere in that chain of getting that device on the market, somebody interacts with it who could introduce something into that process of getting the device manufactured, bought, purchased, pieces of software found, people into the system that have got access to the IT department. All those other factors start to kick in, so it's not just whether the devs and the security team have done their job. Other factors in the business come into play. So it's now a whole business process problem. And I've got to look at that from everything from the initial development, all through the procurement manufacturing cycle, how it goes out to customers, how it gets maintained and the impact back across the system, and ultimately to its end of life. And when it comes off the market, meeting regulation for end of life and actually ensuring that it can't get back into the system, how it gets removed from our platform, all those factors start to kick in. And like I said, it's now a problem which isn't just the devs' problem. Okay, they will shoulder the blame because they're the ones that understand it, but it's not actually all their problem. Everybody's involved. All right, let's have a look at some examples then. I've got a few to look at which introduce a few ideas. So, very interesting one, largely because they chose a particularly high-profile brand of vehicle which uses lots of technology and everybody loves, but actually it had nothing to do with the car in reality. It was all to do with Bluetooth. And in this case, you could argue that as far as the devs were concerned, they did their job properly. They've implemented secure boot, they've implemented secure firmware update correctly, they've done all the key handling mechanisms correctly, they've got everything in place. Okay, so they've done their job correctly. Where it kind of fell down a little bit potentially is they forgot about humans, right, in the design model. And the fact that humans are basically lazy and they like certain things to happen, especially when it comes to their cars, and they like convenience. I don't know if you've got one of these cars that does this auto open when the key arrives. Yeah, I turn mine off. Don't know why, I just like to press a button and know it's me opening my car and driving it away. But convenience kicked in, okay? And then there's this, if you don't fully understand the mechanisms by which that data is being passed to the car, well, that's what got found. Somebody exploited a Bluetooth vulnerability to actually pass data and do a very old trick in RKE systems of doing man-in-the-middle exploitation. Oh, sorry, person-in-the-middle exploitation, to be correct. Which is an old trick which got exploited on Bluetooth because somebody worked out how to get around all the systems that had put in place. Okay. So while the devs have done most of their job, actually not completely. They didn't do all of the modeling of all the factors of things that might kick in. So another attack then, this is a huge one, and you can find more information on this on the web than is sensible. SolarWinds. And again, we can argue they did their job properly. The devs have done pretty much everything correctly. They've got mechanisms to deploy code, they've got mechanisms to test it, they've got keys in place, they've got certificates in place, they've got everything that's in place except managing the development cycle within the company that got hacked, which is kind of the new way of getting in. Once you've solved everything else, you find a new door to entry. So in this case, a piece of Trojan code is added to their build process that opened a command and control server back to the attackers after it had been deployed. But as far as the updates were concerned to the end systems, it's valid. It's been certified, it's been signed, it's deployed correctly, it's coming from a valid location. It doesn't know what the code is, it only knows that it's valid and authenticated in the build. So, kind of the devs have done most things right, but this time sort of system and process failures kind of kick in, which again adds to things that we have to think about looking at. And another great one, I got this while I was on holiday. So this is from LastPass. So it's a similar vein of attack, really. We're really sorry, but our development process has been hacked. And somebody's stolen the code, but we think we're secure. I'm like, well, great, because that's got access to everything I can't remember in the way of passwords. So now you're kind of worrying, okay? So they've been very good, and they've dealt with it, and they don't think anything's compromised because they don't hold your key, thankfully. But people now know how they put it together, and will be finding exploits and way around it, because that's the way the world works. So in this case, actually, the devs have probably done everything right. The code base being stolen, well, that's kind of a new and interesting one, which comes to the other side of it, which is social engineering side of security, where people have got access to the building through somebody's access to the system. So it becomes kind of IT and HR and other systems kick in place that, hang on, all the factors in the company have got an impact on the security of the end product. So it's not just the devs. Okay. So it comes to this idea. Secure boot becomes the keystone. If I don't have secure boot, the rest of it's pointless because the arch falls down. If I've got secure boot and I don't have the other things, it might lean to one side and it might work, but I've left a vulnerability open. So saying I've got a part with secure boot is great. It's part of a process. But lots of other factors kick in. If I don't have all the other things in place and don't seal all of those up and don't manage all of those processes, then something else leaves a vulnerability to be exposed, which I then have to manage. So it now becomes this whole business process. Again, it's down to equally, I can have all of this in place and the devs can be doing their job, but if these two bits at the bottom aren't managed, okay, if we've got poor leadership and we've got an incorrect mindset because we kind of tick box in and we're not really doing security, we're kind of saying we're doing security, which are two very different things, then again, not a very solid foundation for the archway. So all the other things can be great, but if the people who run the company aren't interested, it becomes a problem. So everybody has got a role to play in this system, okay, which is where it basically comes down to. Which gets me to this one, okay, and I'm going to make it a big slide because it's a little bit easier to read. It probably isn't actually looking at the back. Can you read it? Maybe. All right. It's my view of most of the processes if we want to make this system run. So we have products along the bottom, okay? And they have hardware revisions. And on each of the hardware revisions, we have multiple software revisions. And we've got to manage all these in the field, remember, because we've just deployed 1 million products, right, of various devices. And then we've got multi-million products across different product families, all run by this same dev team. So I've got to manage all of those. Oh, hang on. They've all got an app involved, and they've all got a cloud back end. And I need to manage keys for all of those. And I need to manufacture them. Hang on a second. Anybody see any clashes that potentially might happen here and things go wrong? Okay, so it becomes an issue. Somewhere in all of this, I've got to manage keys. Okay, and of course everybody's got keys. Everybody knows exactly who runs their keys, who's got access to them, where they're stored, how they derive them. Does everybody know all those things? Okay, so that's pretty crucial. How do I procure them and how do I get them put onto parts? Okay, any potential vulnerability points? I'm in manufacturing. Do the manufacturing guys really care? Not really. But if you help them understand they're part of a process that keeps the company functioning, then maybe they will. Anybody ever see any difference between embedded software development and apps and the cloud? Okay, very, very different. Okay, very different in how I then want to deploy parts, how I think about writing code, how I interact with it. All of that comes behind tools that are coming in. So we've got a lot of talk and work we've been doing on SBOMs recently, hence the paper John was talking about earlier. But if we look at things like software composition analysis tools, they're great for open source, they're great for apps and cloud, not quite so good yet for embedded code. Okay, so there's a little bit of manual work to do, but we want to get rid of that manual nature of it because that's not very good for finding and automating these problems and doing regression tests and regression builds. And we've got to have that automated because we've got to try and reduce the burden on the devs. And ultimately, the devs need to do their job and get interjected when these vulnerabilities kick in. And I have all these other outside influences that I've got to manage. I've got to manage CVEs coming in. I've got to manage vulnerabilities. So it gets a very complex diagram of this whole company has got to manage it to keep making money. And it's not down to the devs and the software team and the security team. It's everybody. Okay. So it means a little bit of a change of thought processes. All right, so that's me done. Ultimately then, quick summary, secure boot becomes a key function in the system. Okay, the rest of it's pointless if we haven't got it because we can't get integrity at the end device. There is legislation that's going to start driving it, and how you read it and how you interpret it sort of gets you to this point where you go, actually all these things need to be in place. We're going to start needing to think about this. So it becomes a very crucial part of secure by design. But it's heavily reliant on other processes. It in itself does not solve it. It is part of a complex set of cascading effects that need to be looked at. In all of this, key management is critical. Okay? keys on a USB stick in the boss's desk is not the way ahead. Because if the boss leaves, he takes the keys with him, we can't make anything, which might be his plan, you never know, okay? But ultimately, they are the critical part of it. If we don't know where they are, how they get derived, who manages them, who's got access to them, important, okay? So it comes to that point, getting secure boot right is a big challenge, because it on its own is not one thing, it's a cascade of effects. And it is a team game. Everybody's got a part to play. All right, thank you.